Welcome to Understand Chemistry. This is Dr. Bilal. In my last video, I explained various polymerization methods focusing on the two major categories, step growth and chain growth polymerization, and explored the major differences between them. In this video, I will comprehensively cover one of the most significant polymerization methods, the step growth polymerization. This method comprises two types, polyaddition reactions and polycondensation reactions. So let's begin with the key characteristics of step growth polymerization. The major characteristic of step growth polymerization is that the monomers must have two or more functional groups. Otherwise, polymerization will not happen. For example, let us consider a reaction between two monofunctional reagents, acetic acid and ethanol. They both will react with each other and produce ethyl acetate and water. The reaction ends here and no polymer is produced. Now let us see if we get polymer or not if reaction happens between monofunctional and bifunctional reagents. As an example, consider the reaction between acetic acid and ethylene glycol. They react with each other to form new product, but they will not produce polymer. Now consider another case where we have only bifunctional reagents. In this case, both bifunctional monomer react with each other to produce polymer. For example, adipic acid reacts with ethylene glycol stepwise to produce polymer. In step growth polymerization, no initiator is needed, and the reaction occurs between functional groups of monomers. In this type of polymerization, the reaction goes stepwise, means first the reaction happens between monomers to produce dimer and trimer, then these dimer and trimers and monomers are combined to produce oligomers. In the end, oligomers are combined to produce polymer. The step growth polymerization has two types, polyaddition reactions and polycondensation reactions. In polyaddition reaction, reacting species such as monomer or oligomers react to produce an adduct without releasing any byproduct. On the other hand, in polycondensation reaction, the reacting species react to produce a product and a living molecule, such as water or alcohol. Let us see first the polyaddition reaction. As shown before, in polyaddition reaction, the reacting species Pi and Pj are combined to produce polymer without releasing any byproduct. In this equation, Pi and Pj denote chains of degree of polymerization I and J respectively. Now, let us talk about polyurethane formation, which is an example of polyaddition reaction. Polyurethanes are the polymer containing urethane functional group in their main chain. Polyurethane is formed by reaction of diisocyanate and diol. Let us see how mechanism of urethane formation works. For clarity, imagine using a monofunctional isocyanate and a monofunctional alcohol. We know practically polyurethane is produced from bifunctional monomers. But this simplified model helps you to understand each reaction step. The first step in the mechanism is the nucleophilic attack. The oxygen in the alcohol has a lone pair of electrons, so it acts as a nucleophile and attacks the electrophilic carbon in the isocyanate group, which is electron deficient because both the nitrogen and oxygen pull electron density away by inductive effects. Because of this attack, tetrahedral intermediate is formed. Once the tetrahedral intermediate is formed, electrons shift between the nitrogen and oxygen atom, and this resonance helps to distribute the charge, thereby stabilizing the intermediate. The process occurs because the electron delocalization lowers the overall energy of the structure. After the intermediate forms, a proton is transferred usually from the hydroxyl group to the nitrogen atom, and this movement of protons stabilizes the molecule, resulting in the formation of the urethane group, also called carbamate group. In the synthesis of polyurethane, a diisocyanate which contains two isocyanate groups react with diol that has two hydroxyl groups, and each isocyanate group is attacked by a hydroxyl group in a manner similar to the single molecule reaction. As a result, a urethane linkage is formed at each reaction site, and the process continues as more monomer, dimer, trimer or oligomers react with each other, thereby building a long polymer chain with reacting urethane units. This overall process is classified as step growth or polyaddition polymerization because it involves the gradual linkage of monomer without the elimination of small byproduct. Here is an example of polyurethane formation where 1,6-diisocyanohexane reacted with butane 1,4-diol to produce polyhexamethylene butylene urethane. This is the example of aliphatic polyurethane. In contrast, aromatic polyurethane is formed when a bis-4-isocyanophenoylmethane reacts with the butane diol. Formation of polyurea is another example of polyaddition reaction. Polyurea are the polymers containing urea repeating unit in the main chain. Polyurea is formed by the reaction of diisocyanate and diamine. Let us understand the mechanism of formation of urea with help of simple molecule that contain only one functional group. The formation of urea from an amine and isocyanate follows a nucleophilic addition mechanism, where the amine reacts with the electrophilic carbon of the isocyanate. Let's break down. Step 1 in this mechanism is the nucleophilic attack. The amine has a lone pair of electrons on the nitrogen atom, making it nucleophilic. It attacks the electrophilic carbon in the isocyanate, leading to the formation of a sweeter ionic intermediate, where the nitrogen becomes positively charged and the oxygen takes on a negative charge. The intermediate can show resonance because the negative charge on the oxygen atom can delocalize. This means the negative oxygen can shift its lone pair towards the carbonyl-like bond, pushing the electron density towards the nitrogen. This stabilizes the intermediate temporarily until proton transfer occurs. In the next step, the proton from the positively charged nitrogen is transferred to the negatively charged oxygen, leading to the collapse of the intermediate. As a result, the final product, urea, is formed. Now, let us take bifunctional monomer to see how polyurea is formed using this mechanism. When a bifunctional monomer is used, polyurea forms through a step growth polymerization mechanism where repeating units are linked to urea bond. Each amine group attacks the electrophilic carbon in the isocyanate, forming a carbamic intermediate, similar to the one formed in the monomeric urea synthesis. This intermediate stabilizes through resonance, briefly distributes the electron density among nitrogen, carbon, and oxygen. In the next step, the negative charge on oxygen from the reaction intermediate receives a proton, completing the formation of urea linkage. Because both the amine and isocyanate have two reactive groups, the reaction continues in both directions, forming a long chain polymer, where urea linkage repetitively connect bifunctional monomer. The process repeats until polymerization halts due to complete consumption of the reactive functional group. The result is polyurea. An example of polyurea is shown here. In this reaction, 1,6-diisocyanohexane is combined with hexane 1,6-diamine to produce polyhexane 1,6-diurea. Let us proceed to our next example of polyaddition reaction. Epoxy resin curing also follow a polyaddition mechanism, where a di-epoxy molecule containing two epoxy groups reacts with a diamine molecule containing two amine groups. This reaction proceeds through repeated nucleophilic attacks and proton transfers, ultimately forming a cross-linked polyepoxy resin network. Let us see how the reaction proceeds. In the step 1, nucleophilic attack on epoxide. The amine from the diamine act as nucleophile attacking the electrophilic epoxide group. This leads to the formation of alkoxide intermediate, where the oxygen becomes negatively charged. The negatively charged oxygen abstracts a proton from another amine or solvent, stabilizing the intermediate and leading to the formation of hydroxyl functional group. At this point, the epoxy ring is fully opened and the nitrogen is now covalently bonded to the former epoxide carbon. Since both the di-epoxy and diamine molecules are bifunctional, this process continues at both reactive sites, leading to the long chain polymerization. Each amine group reacts with an epoxide, creating an extended polymeric structure. The hydroxyl groups formed during the reaction contribute to the additional cross-linking and improve adhesion and mechanical properties. As the reaction progresses, the epoxy polymer grows into a fully cured three-dimensional network. The extent of curing depends on the stoichiometry, temperature, and curing time. The final thermosetting polymer is highly durable, chemically resistant, and mechanically strong. An example of epoxy amine polymer is shown here. In this reaction, diglycidyl ether of ethylene glycol react with ethylene amine to result epoxy amine polymer. Let us proceed to the second type of the step growth polymerization, the polycondensation reactions. Polycondensation is a step growth polymerization. Here are core principles of polycondensation reaction. The first one is that the monomer must have at least two reactive groups such as hydroxyl, carboxylic acid, or amine group. The second one is the release of small molecules such as water, HCl, or methanol. An equation of polycondensation reaction is shown here, where Pi and Pj denote chains of degree of polymerization I and J respectively. The value of I and J can be 1, 2, 3, and so on. Since polycondensation reaction is reversible in contrast to polyaddition, therefore, continuous removal of the byproduct is necessary in order to move the reaction to forward direction, according to the Chatelier principle. Examples of polycondensation derived polymers are polyesters, polyamides, and polycarbonates. Polyesters are formed via condensation reaction between diacid and diols. The polyamide arises from the reaction between diamine and diacid. Polycarbonates are synthesized by polycondensation of compounds with carbonate groups. I will discuss one by one each class of polymer in detail with example. Let us first talk about polyesters. Polyester is a polymer composed of repeating ester bonds. Polyesters can be produced by the self-condensation of hydroxy carboxylic acid. These are the molecules that contain both hydroxyl and carboxylic acid groups. Alternatively, when a dicarboxylic acid reacts with a diol, they form ester bonds through a condensation reaction, yielding the polyester while releasing water as a byproduct. The key challenge in this polymerization is the removal of water, which has high boiling point and is difficult to eliminate. The solution to this problem is the use of activated carboxylic acid. By using activated dicarboxylic acid, the volatile or gas-like side products such as methanol or HCl will be produced that can easily leave the reaction. One of the most common route of synthesizing polyester using activated dicarboxylic acid is the acid chloride route. According to this, The dicarboxylic acid is first converted to diacid chloride by reaction of diacid with thionyl chloride. Then this diacid is allowed to react with diol to produce polyester. The side product is HCl. There are several advantages of this reaction. The first one is HCl is a gas that leaves the system readily, enabling a nearly irreversible reaction pathway. And this reaction also proceeds rapidly under mild or room condition, enhancing its efficiency. Beside advantages, this reaction has also some limitations. The first one is the acid chlorides are highly moisture sensitive. Even small amount of water can hydrolyze them back to carboxylic acid. Furthermore, the HCl gas produced can be corrosive to equipment and might require neutralization or specialized handling to mitigate equipment damage. Another method of synthesizing polyester using activated diacid is trans-esterification. The process of using methyl ester to react with alcohol to give another ester is called trans-esterification. In case of bifunctional monomers, where several trans-esterifications occur to produce polyester is called polytrans-esterification. A general polytrans-esterification reaction is shown here. In this reaction, a dimethyl ester reacts with a diol to produce polyester or an aliphatic polyester. In this reaction, methanol is produced as byproduct. Methanol has a boiling point of 65 degrees Celsius, making it easier to evaporate compared to water. A well-known example of this process is the formation of polyethylene terephthalate, an aromatic polyester produced by reacting dimethyl terephthalate with ethylene glycol. Now, the question is how to remove methanol from the reaction mixture. In a bulk polymerization setup, the reaction is carried out without any solvent. In this case, methanol can be directly removed by applying vacuum or by sweeping with an inert gas. The continuous removal of the methanol shifts the equilibrium to favor polymer formation. However, when the reaction is carried out in a solvent, we need to remove the side product without losing the solvent. This is where azeotropic polycondensation comes into play. In azeotropic polycondensation, the solvent forms an azeotrope with the byproduct, such as methanol, allowing it to be continuously removed by distillation while the solvent remains in the reaction mixture. This strategy helps drive the reaction to completion without sacrificing the solvent. The necessary condition for this process is that we must choose a solvent that forms azeotropic mixture with the byproduct. Let me show you some example of azeotropic mixture. But first, understand what is meant by azeotropic mixture. Azeotropic mixture is a liquid mixture that boils at a constant temperature, maintaining the same composition in both the vapor and liquid phases. For example, toluene and methanol. Toluene and methanol form azeotropic mixture in a composition ratio 72% toluene and 28% methanol. Their azeotrope has a boiling point of 62.6 degrees Celsius, which is lower than individual component of the azeotrope. Similarly, toluene and water makes an azeotrope where toluene is 79.8% and it boils at 84 degrees Celsius. Another well-known example of azeotropic mixture is tetrahydrofuran and methanol, where in the composition of azeotrope, 94% is methanol. This azeotrope boils at 64.6 degrees Celsius. The key step in removing the side product by azeotropic distillation is solvent recovery. Let me explain you how to remove the byproduct and recover the solvent. First, the reaction mixture is heated to the boiling point. The vapor that condenses is a mixture of both the solvent and the byproduct. Active molecular sieves are then used to trap the byproduct selectively, thereby separating it from the solvent. The purified solvent is subsequently returned to the reaction mixture. Now let us talk about polyamides. Polyamides are the polymers characterized by amide linkages. They are generally produced by the condensation reaction between diacids and diamine. Synthesis of nylon 6,6 is a well-known example of polyamide produced by polycondensation reaction. In this reaction, hexamethylene diamine and adipic acid are combined together through amide bonds while releasing water as byproduct. Because water is not easily removed, this route can be somewhat challenging. The alternative route for producing polyamide is using activated diacid, as was used in case of polyester. In this method, the diacid, for example adipic acid, is first converted into a diacid chloride by reaction with thionyl chloride. The resulting diacid chloride reacts with the diamine. The nucleophilic amine attacks the carbonyl carbon of the acid chloride, forming the amide linkage. This reaction produces polyamide and liberates hydrogen chloride as the byproduct. Polycarbonate is another class of polymers that follows step growth mechanism. Polycarbonate is a thermoplastic polymer containing carbonate linkages in its backbone. It is known for its strength, transparency, and high impact resistance. In the classic route, bisphenol A reacts with phosgene to produce polycarbonate. The reaction proceeds relatively quickly under mild reaction conditions. However, phosgene is a highly toxic gas and its use requires strict safety measures. Another way of obtaining polycarbonate is trans-esterification of bisphenol and diphenyl carbonate. This route is considered as more environmentally friendly. In this process, diphenyl carbonate acts as the carbonate source. The hydroxyl group of the bisphenol A perform a nucleophilic attack on the carbonyl carbons of diphenyl carbonate, resulting in the exchange of ester group. This exchange of ester is known as trans-esterification, as discussed before. The byproduct phenol has a relatively low boiling point and can be efficiently removed from the reaction mixture to push the equilibrium toward polymer formation. Let us discuss the kinetics of polycondensation reaction. To understand the kinetics of step growth polymerization, let us consider polyesterification. In the case of polyesterification, a diacid A and a diol D are reacting in equimolar concentration without any external catalyst. The rate of polycondensation is equal to the rate constant into square of the concentration of A into the concentration of D. Now the question is why there is A squared in the rate expression. Actually, in many polycondensation reactions, the diacid acts as an autocatalyst. This means first A acts as a proton donor. Here it is acting as catalyst. The second A reacts with hydroxyl group to form the ester. Here it is acting as monomer. When the concentration of A and D are equal, the rate law simplifies to Ka cube. To obtain the concentration profile over time, we applying definite integral from concentration A naught to At and time t0 to t. We get 2 kt 1 over At squared minus 1 over A naught squared. Now let us see how to write this expression in terms of extent of reaction, P. If P represents the fraction of functional group that have reacted at time t, then P mathematically can be written as, simplifying this expression for At, we get At is equal to A naught into 1 minus P, where 1 minus P represents unreacted functional groups. Placing the value of At in the last equation, it will take the form as shown here, which on simplification will take the form as shown. This is an important equation. It tells us that a plot drawn between 1 over 1 minus P whole square will be a straight line having slope 2A naught square times K, the rate constant. Solving this equation for P, we are ended up with this expression. From this equation, we can say that at time t is equal to 0, P will be equal to 0, means there is no reaction, and after infinite time, P is equal to 1. This indicates a complete conversion. Now let us see how to find degree of polymerization. The number average degree of polymerization is equal to the number of original molecules divided by number of molecules at a specific time t. We can write degree of polymerization is equal to n naught over nt. That will be equal to a naught over at. By placing the value of at as described before, we get number average degree of polymerization equal to 1 over 1 minus p. This equation is known as Carothers equation. It was named after Wallace Carothers, who pioneered the understanding of step growth polymerization. A graph is plotted taking conversion P as x-axis and the degree of polymerization as y-axis. At low conversion, the curve is nearly flat, indicating minimal chain growth. But as P increases, the gradual rise reflects the incremental buildup of polymer chains. As the reaction nears completion, when P is close to 1, the curve steeply rises due to hyperbolic nature of 1 over 1 minus P, meaning that even small increase in conversion can cause dramatic jump in the chain length. Let us understand this concept by taking three different values of P. If the value of P is 0.5, the degree of polymerization will be 2. Means on the average there are 2 monomer units per chain. If the value of P is 0.9, the degree of polymerization will be 10. And if the value of P is 0.99, the degree of polymerization will be 100. This indicates how crucial is the parameter P is to achieve polymer of high molar mass. This graph not only demonstrates the need for high conversion to synthesize high molar mass polymer, but also highlights the importance of precise reaction control. Let us consider the kinetics of uncatalyzed polycondensation. To understand reaction kinetics, we start with the rate equation. In this case, the rate of polycondensation is proportional to the product of concentration of A and concentration of D. Since we assume that A is equal to D, we simplify this to minus dA over dt is equal to Ka square. Next, we separate the variables and integrate within the appropriate limits. After integration and substitution, we arrive at Kt is equal to 1 over At minus 1 over A naught. Now we substitute At is equal to A naught into 1 minus P into our equation. Rearrangement gives A naught Kt is equal to 1 over 1 minus P minus 1. Since degree of polymerization dPn is defined as dPn is equal to 1 over 1 minus P. So we can write the last expression as dPn is equal to A naught Kt plus 1. This equation helps us to understand how polymer growth progresses over time. Now take a look at the graph. This plot shows the degree of polymerization versus time at different temperatures 20, 30 and 35 degrees Celsius. What we can see here is that as temperature increases, the rate of polymerization also increases, leading to a higher degree of polymerization in less time. This illustrates the impact of temperature on the reaction kinetics. Now let us see how to calculate number and weight average molar masses and polydispersity index or dispersity in step growth polymerization. In step growth polymerization, Carothers equation provides a straightforward way to connect the reaction conversion P with the molecular characteristics of the polymer. First, the number average degree of polymerization is given by dPn is equal to 1 over 1 minus P. meaning that on average each polymer chain contains monomer units equal to dPn. This means multiplying the degree of polymerization with the molar mass of repeating unit m0 gives the number average molar mass. Mn is equal to m0 over 1 minus p. To account for the greater contribution of longer chains to the overall mass, the weight average molar mass is determined by multiplying m0 with the weight average degree of polymerization. The weight average degree of polymerization defined by Carothers is equal to 1 plus p over 1 minus p. By multiplying m0 with the weight average degree of polymerization, we get weight average molar mass. Finally, the poly dispersity index or dispersity, which quantifies the breadth of the molecular weight distribution, is the ratio of these two averages, which is simplified as 1 plus p. Thus, as the conversion p increases, both Mn and Mw rise dramatically, and the PDI approaches 2 when p nears 1, indicating a broader distribution in chain length. In the end, let us talk about modified Carothers equation. From the Carothers equation, we know that for the value of p equal to 1 under normal condition, when the functional groups have same molar ratio, we obtain very high molar mass polymer, which is difficult to process. In order to avoid that much high molar mass polymer, it is required that value of p should be reduced. This can be done by using slight excess use of one of the reactant. This means by using non-stoichiometric monomers. When there is no stoichiometric equivalence, the Carothers equation is no longer valid. For this, modified Carothers equation is used, according to which dPn will be equal to 1 plus R whole divided by 1 plus R minus Rp, where R is the ratio of the moles of limiting groups and the moles of excess groups, and its value is always less than or equal to 1. For equimolar ratio of functional groups, value of R is equal to 1. By placing this value in modified Carothers equation, we get dPn equal to 1 over 1 minus p, which is again Carothers equations. This means when R is equal to 1, the modified Carothers equation and Carothers equation gives the same result. Now let us understand how slight change in the stoichiometry made big difference. Suppose for a reaction, when we use equimolar concentration of both functional groups, let us calculate the dPn when p is equal to 0.995. By placing the value in any of this equation, we get dPn is equal to 200. Now consider a non-stoichiometric system. When functional groups A is equal to 0.97 moles and B is 1.0 mole, then the value of R will be equal to 0.97. Again, for the p value equal to 0.995, let us calculate dPn. By placing the value in modified Carothers equation, we get dP degree of polymerization is equal to 66, which is far less than the degree of polymerization when equimolar functional groups are used. This is how degree of polymerization could be controlled. If you have any question regarding this topic, please consider the comment box. Thanks for watching.